Hi all, welcome to Anu's Chem Corner. In today's video, we are diving into one of the most challenging topics in our chemistry syllabus. That's none other than acid-base titration. I know many of you have been asking, why do we use different equations for the same titration? Well, I'm here to clear all those doubts and make sure you understand exactly what is happening at each step. We will also break down the titration curves and graph. I will walk you through the pH changes at every stages. So you can see exactly how it all works and what do you expect in your exam. So if you have been struggling with this concept or just want to get a deeper understanding, stick around. By the end of this video, you will get all the idea. All of your doubt will be cleared. So let's get into the video. Here we go. So in this video, as I told you, we are concentrating with the titration. So make sure before doing this one, you are already familiar with the concept of buffer and salt. If you are not familiar, check my videos of buffer and salt concept. Okay. So let's move on to the titration. So actually, what is this titration? What is the purpose of titration? Okay. The purpose of titration is just calculating the concentration, unknown concentration. Okay. For example, this is the actual experimental picture of this one. Okay. The titration, acid base titration. Suppose you don't know the concentration of some acid like HCl. So the molarity of HCl is your unknown thing. So you have to calculate this molarity. So that is your purpose. For that, what you have to do is you are going to titrate with some base. Okay. So your unknown thing, you can take it in a conical flask like this. You can pipette out like some specified amount you are taking, like some 20 ml or 30 ml, like that. You can measure that analyte. So why I'm called analyte? Because this is the unknown concentration. Okay, so the analyte you are taking in a conical flask and you are adding a non-concentration base from the burette. Okay, if the non-concentration and it is taken in a burette, then that is what we call titrant. So in this case, for an example, I am just taking NaOH as a titrant. Okay, so NaOH concentration, you know the NaOH concentration molarity. Okay, and you are adding 1 by 1 ml like that to this conical flask. So what happened? Finally, like when you are adding 1 ml or 2 ml, what happened? NaOH is the limiting reagent because this much of HCl is there. So NaOH may be the limiting reagent, but there will be a point when both are limiting reagent. Correct? Suppose our mixture contain 5 mole of HCl. So when you are adding again 5 mole of NaOH, what happened? At that time the solution is completely neutralized. Correct? So that is our end point, the complete neutralization. Or you can say both are limiting reagent. So if HCl is 5 mole, then you need NaOH also as 5 mole in order to get the limiting reagent. Both are limiting reagent point. Okay. So you are added 5 mole of NaOH. So you can calculate. If you calculate the number of moles of NaOH by using the molarity and volume. Alright. Volume of NaOH is equal to the molarity volume times molarity of NaOH will give the number of moles of NaOH, isn't it, which is equal to the molarity and volume of NaHCl. Correct, because that is nothing but number of moles of HCl. So you can use this equation only when 1:1 ratio, right? Because suppose this HCl is not HCl like H2SO4, then you need one H2SO4 required 2 NaOH for the reaction, complete neutralization, isn't it? Okay, so that if 5 moles of H2SO4 is there, in order to get complete neutralization, you need 10 mole of NaOH. So do not believe like always number of moles of base is equal to number of moles of H2SO4. No, no. It's also only possible in 1:1 ratio. So only 1:1 ratio you can use V1 M1 V1 is equal to like M1 V1 is equal to M2 V2 is only possible with a 1:1 ratio. Otherwise, simply you can use number of H plus times M1 V1 is equal to number of M1 M2 V2 times number of OH minus. This equation you can use everywhere. Okay, so here number of H plus means our acid, like see H2SO4 means 2 is the number of H plus and NaOH means just 1 only, so OH minus will be 1. Okay, in that way, See, H plus is there and M1 is the unknown quantity. V1 we are already took some volume, so that you can plug, and M2 we are already familiar, and V2, for getting the V2 we are actually doing this titration, because how much volume you are added to get the endpoint, exact endpoint, correct? So that volume is like we are determining through this titration. By getting that one, you can just simply calculate the molarity. That is our purpose of this titration. Okay, but there maybe you got confused. How do you know the endpoint is reached? Correct? How do you know now the exact neutralization is done? That's the indicator role, right? So before doing this titration, before you are adding the NaOH from the burette, you are adding some indicator. 1 or 2 drops of indicator is added. So when you are add an indicator, the thing is they will change the color. Okay, you can select the indicator, appropriate indicator. So when that end point, like at the complete neutralization point, they will change the color of the reaction medium, like the conical flask solution. Okay, so at that time, when there is a color change, you can stop the titration. Just take that burette reading. That is our volume of NaOH. Okay, so for 1 is to 1 equation, you can 1 is to 1 ratio, you can just simply use M1 V1 is equal to M2 V2, and you are substituting every values, so that you can find out the molarity of HCl, or molarity of the acid or analyte. That is the usual procedure. Okay, right. But in this video, we are not ourselves with this kind of thing, because this is nothing, we are just applying this molarity. What our interest is the pH calculation. In each of these titration stages, what are the changes in pH? Who determine the pH? Right? Who contributing to the pH? How do you calculate the pH? Which equation we need to use? Those are the questions in front of us. Okay, so let's see stage by stage. Okay, so here we are first dealing with a strong acid, strong base titration. Okay, strong acid, strong base titration. So first case, as an example, I am just taking HCl and NaOH. So the reaction, NaCl and H2O is formed. So here I am giving the molarity, because I told you what my purpose to get the idea about pH. Who determine the pH like that? So I am giving the concentration of both the stuff, like 5 molar 1 liter HCl. Suppose I have. So initially I have 5 mole of HCl. Okay, so the first stage of titration, like initial point, if you are not added any NaOH, so at that time, who is there in the reaction medium, or who determine the pH, right? If no NaOH is not there, there is no reaction, right? So the reaction medium only contain the HCl. The reaction medium means what we are taking, like in conical flask. Okay, conical flask is our reaction medium. HCl is the only present thing. So who determine the pH? HCl will determine the pH. How to determine the pH? You know that HCl is a strong acid. Have to study the list of strong acid. Okay. So HCl is a strong acid. So definitely you can take the negative logarithm of the concentration of HCl itself. Like here it is 5 molar, the same initial concentration you can take. So what is the equation for this stage? Negative logarithm of H plus initial concentration. In this case it is 5 molar. Correct? Okay. It's simple. Then you just tell me, if 2 mole of NaOH is added, what happened? Who determined the pH? If 2 mole of NaOH is added, who determine the pH? So what is our equation? HCl is there. So every time in titration, be careful. This table is very, very important. Every time in titration, this table is very, very important. What is this table? Before reaction, after reaction table, or BCA table. Okay, but here the change I am not taking, just before reaction, after reaction, like that only I am taking. Okay, for simplicity. Okay, initially there are 5 moles of HCl that we already seen, and NaOH, what I told, 2 moles of NaOH is added. So before reaction 0 0. After reaction, before the equivalent point, definitely NaOH will be the limiting reagent. So after the reaction, 0 NaOH will be there and 3 mole of HCl will left, right? So the reaction medium now contain, what are the thing? 3 mole of the conical flask contain 3 mole of HCl as well as 3 mole of NaCl and 3 mole of H2O. So this is our reaction medium. In this reaction medium, who will determine the pH? Definitely HCl, correct? Why? Because there is three things. HCl is there, NaCl is there, H2O is there. NaOH is not in the picture. It is zero. It's completely consumed, right? But in which NaCl and water is neutral. NaCl is a neutral salt. Why NaCl is a neutral salt? As I told you, you have to check with the salt video, right? When a strong acid react with a strong base, you got a neutral salt. So they will not contribute anything to the pH. Okay. So that's why you can tell who determine the pH. Even though the reaction contain NaCl and H2O, you don't want to consider like H2O is okay. H2O, HCl solution we are talking, right? Yes. So who determine the pH? HCl will determine. HCl excess, correct? Not initial. So how to determine the pH? Same, it is a strong acid, so negative logarithm of H plus concentration. Here the H plus concentration is important. What it is? It's not negative logarithm of 3. 3 is number of mole. Always concentration means number of moles over volume. What's the volume? Volume, it's not about 1 liter. See at the top, I told it's 1 liter. 1 liter is the volume of HCl alone. Here, what is the problem? You are already added 2 moles of NaOH, right? So 2 moles of NaOH means that contributes some particular amount of volume. I didn't mention here. So anyway, that volume you have to consider like total volume. So volume of HCl plus volume of NaOH. Okay, that 2 moles of NaOH contributing volume should also have to consider. Correct? So negative logarithm of 3 is wrong actually. That is number of moles only. So negative logarithm of that excess number of moles over V total. That should be the pH. Correct? Okay. Then the next part, like 5 moles of NaOH is added. So at that time, HCl plus NaOH, again, you have to consider every time have to consider that before reaction, after reaction table. Okay, here also 5 and this time it's 5 0 0. This is the before reaction, and after reaction how much it is? Yes, after reaction this is 0, this is 0, this is 5, this is 5. So this is what we called end point. Both the reagents are 0, so that is the end point or equivalence point. Got it? Okay, so here who is in the reaction medium? In the reaction medium there is only NaCl and H2O, right? So who determine the pH? Definitely NaCl solution, right? So what is, as I in the top case I told NaCl will not contribute anything. NaCl is neutral, but here what to do? There is nothing other than NaCl and H2O. So definitely that will be the factor which determine the pH. Okay. So how do you calculate NaOH, NaCl pH? What is NaCl? That's the point. NaCl is a salt. What kind of salt? Is it a basic salt? If it's a weak basic salt, you have to consider the ice table. If it's an acidic salt, you have to consider the ice table. But this time, it's okay. It's just neutral salt, right? So neutral salt means nothing to calculate. It's just 7. That's all. Correct? It's just a 7 only. So no calculations are involved. Just 7 you can write. Okay. After that, see the fourth stage of titration. 7 moles of NaOH is added. Again, you are considering the same reaction. HCl plus NaOH gives H2O plus NaCl, right? Okay, this time what's the before and after reaction table? 5 and this time 7 0 0. This time NaOH is the excess thing, right? So after the reaction, after the equivalent point, HCl will be the acid will be the limiting reagent, correct? Or analyte will be the limiting reagent. So this one is 0, this one is 2, excess is there, and yeah, 5 mole, 5 mole. Here who determine the pH? NaCl and H2O and also NaOH are the reaction medium, but in which, yes, you know that one, NaCl or H2O you don't want to consider, right? So who determines the pH? NaOH excess. How to calculate the pH? It is a base. It's a strong base. So you can calculate negative logarithm of OH minus. This is base. So you can calculate negative logarithm of OH minus concentration. So pH you need, so 14 minus this one. 14 minus logarithm of OH minus. Correct? That's the pH. So what is the OH minus concentration? So in this case, again I'm telling, negative logarithm of 2 is not the OH minus concentration. 2 is number of moles. Number of moles over V total. Now you are added some 7 moles of NaOH, so that makes some volume plus the initial volume of HCl, which is 1 liter. Like that, you have to calculate the OH minus concentration. So a negative logarithm of that OH minus concentration will give a pOH. So 14 minus that pOH will give a pH. So yeah, this is the whole, you got the diagram like the pH curve. So we are starting with this point. See, it's a very low pH, which means it's a strong acid. Since it's a strong acid, the pH value will be very low. And then this is the equivalent point. At equivalent point, who will determine the pH? Salt will determine the pH. The salt in this case is neutral, so that's why 7. After the equivalent point, yes, the reaction medium is basic. Base is the excess thing. So basic pH will be there. That's why it's a strong base. So that's why it's ended like a, like close to the 14th value, 14, pH 14, right? And before the equivalent point, acid will be the excess. Clear? So that's all the titration curve. If you understand this one, here everything is like okay, like it's very simple like that. You can think. But the problem is we are applying the same concept to the second situation. Second situation, it's something complex, like the same concept, but you when I deal that one, you can understand. Okay, so this is our second case: strong base versus weak acid. So the strong base, we are taking the same NaOH, and weak acid, as an example, we can take HF. Okay, so I'm taking the same concentration, 5 molar 1 liter, so that the initial moles of hydrofluoric acid is 5 molar, right? Okay, so let's see the first stage. The same condition, when no NaOH is added, when no NaOH is added, there is only the reaction mixture contain HF, right? So that's our reaction, like no reaction, like on the only the reaction. So let's see. So let's see the second case. So in this case, we are taking strong base versus weak acid. So the same strong base NaOH we can take as an example, and weak acid now we are taking HF. So I'm taking the same molarity as previous case, 5 molar 1 liter, and so that the initial amount is 5 molar HF, correct? Okay, same thing. Unlike is HF and NaOH is the base. Okay, so first case, and no NaOH is added. What happened? Who is there in the reaction medium? Yes, our HF is there as a reaction medium, right? HF is only present there. There is no reaction. So who determine the pH? Definitely HF will determine the pH, correct? Okay, but how to determine the pH? Okay, in the previous case we took like negative logarithm of that 5 initial concentration, right? H plus initial concentration. But do you think in this case is that correct? Here what is the problem? It's a weak acid, right? It's a weak acid. So initially we have 5 molar, but that is not the reaction mixture, correct? If there is a 5 molar HF is there, if it's an HCl, yeah, 5 molar HCl is there. We got the same 5 molar HCl, H plus, and 5 molar Cl minus. So 100% dissociation in case of strong acid. But this time it's a weak acid, right? So it's not 5. Then what it is? How much HF will be there? H plus will be there. H plus concentration is what? It's obviously it's not 5, right? Then how it is, how you have to calculate for a weak acid? Yes, you know, you have to calculate the ice table, right? Consider the ice table instead of sorry, HCl, you can consider the HF ice table, right? Yes, so they will provide the Ka value. So by using the Ka value, you can easily calculate the H plus equilibrium. That H plus equilibrium value is our pH determining thing, right? So that one, so like ice table you can consider. Anyway, the result of ice table, you know that one. Yes, what it is, the x square, here 1 is to 1 ratio, so x will be there, right? So x square over the initial concentration, which is 5 minus something, correct? That x we can omit. Usually we are omit, we are always follow the less than 5% rule, right? So we can omit that 5 minus x, just 5 and Ka value. In that way you can calculate the x. So that x, that is our H plus equilibrium concentration, correct? So that's how we have to do the thing. So see, in the previous one, which was very easy, just negative logarithm of that 5. Here we do some extra step. Why? Because of the reason it is weak acid. We are applying the same concept. This is happening every time. We are applying the same concept, but the problem is this is weak, so we need to do some additional step. Okay, so negative logarithm of H plus equilibrium will be the value. Okay, right. Then the next step, we are adding the same 2 mole of NaOH. So as I told you before, reaction after reaction is very important. Here also 5 mole is the before reaction, and we have 2 mole initially, 0 0, right? So here the formed species is what? The salt is what? HF plus NaOH gives NaF plus H2O, right? So after the reaction there will be an excess of HF, and this will be 0, and there will be 2, and there will be 2, correct? Okay, so at that time who determined the pH? Definitely HF, correct? As in the previous case HCl was the thing, so herely the HF excess, is it correct? So you can calculate the number of moles over volume, so that will be the new initial concentration. Like that, can you able to take the ice table? Is it the way you are calculating? If you are, is that the way? You are wrong. Is it? Here what is the problem? Here not only the HF, NaF is also there. In previous case also HCl and NaCl was there, but we ignore the NaCl. Why? Because it is a neutral salt. But this time, is it a neutral salt? No, this is a weak acid, and the other one is strong base, right? Weak acid, strong base means the salt is not a neutral salt. It has some effect, isn't it? So some basic character will be there. The salt is, since this one is strong base and this one is weak, definitely there will be some basic character. The salt is not a neutral, it's a basic salt, a weak base salt. Okay, so not only HF and F minus. Okay, Na I don't want to consider because you know the salt concept. If you are not aware, you just see my video of salt. Okay, Na plus you don't want to worry about it. It's a neutral salt, like neutral ion, Na plus. So you can think about the basic salt. Why it's basic? Because of the F minus. So that's why I took only F minus. Okay, so HF and F minus mixture will determine the pH. What is this HF and F minus mixture? Do you familiar with this mixture? Yes, it's a weak acid and its conjugate base. Weak acid and its conjugate base. That is nothing but buffer, right? So here buffer is there. In the previous case there was no buffer because there is no presence of base, like basic salt, correct? So that's the problem here. So since it is buffer, you can use the Henderson-Hasselbalch equation. So pH is equal to pKa plus log base concentration over acid concentration. So what is our base concentration here? Is it the NaOH base concentration? No. Base means this is our base, right? F minus is our base. This is our buffer. HF F minus is our buffer. So yes, HF Ka value you can take. That they will give the Ka value. So you can take the negative logarithm of Ka. That will give the pKa. And then log base concentration. So what is base concentration? F minus. So it is 2. Is it 2? No. Actually, 2 over 2 is the number of moles, right? 2 over V total, which means you are already added some NaOH. So the V total, as we done in previous case. Similarly, acid means 3 over V total. But in this case, V total will cancel out. So that's why in this case, you can consider just molar ratio, right? It both are same. So you can just calculate, you can just consider the molar ratio of the base over acid. In that way, you are going to calculate the pH. Okay, that's it. Right. And then let's see if any doubt with the buffer concept. Yeah, you please check with my buffer video. All the doubt will clear. Okay. Then what happened if 2.5 moles of NaH is added? So let's see. Here before reaction 5, this one is also 2.5, and 0, 0 after reaction 2.5, 0, 2.5, 2.5. So who determined the pH? Definitely HF and F minus. Same thing. Buffer is formed. So here also you can use the Henderson equation. So which is equal to pKa plus pKa. pH is equal to pKa plus, but what happened to this ratio? Log, as I told you, base concentration, you can just consider the number of moles. So here 2.5, here also the excess moles of HF is 2.5. So 2.5 cancel. Log 1 is equal to 0, isn't it? So this time you can say pH is equal to pKa. That's the importance of this point. So when pH is equal to pKa, or the excess concentration of acid which is equal to the salt formed number, then this point is what we called half equivalence point, or simply halfway point. Okay, simply halfway point. So very important in titration, halfway point. So whenever halfway point is there, you can simply take pH is equal to pH is equal to pKa. Clear? Okay. Then 5 mole of NaOH is added. What happened? 5. Here also 5. Here also 5. 0, 0. And after the reaction, this is 0. This is 0. What is this point? This is our end point of the titration, right? Both are equivalent point. That is end point. Sorry, both are limiting reagent. That is equivalent point. Correct? Okay. After the reaction, here this is F. Here this is F. So who determines the pH? Every time end point, the determining agent is like factor is the salt, right? Here the salt is NaF. In previous case we done salt, so pH is equal to 7. We don't want to do any calculation, but this time is it possible? Right, you know that answer, right? It's not possible here. This is not a neutral. So this is what? How do you calculate the salt pH? Yes, so you have to think about the character. This is a weak base. The salt we have is weak base. How do you calculate the pH of a weak substance? Yes, you have to consider the ice table. What is the ice table of NaF? NaF dissociation you have to think about. NaF means, again I'm telling, NaF, Na you can omit. Why? Because Na plus is negligible, right? It's a neutral ion. So F minus is the factor. F minus is causing a weak basic character. So what is the F minus reaction? F minus reaction, see the problem is if it's a weak acid like HF, what is the acid dissociation equation? You can simply write like H plus plus and F minus. There is no doubt maybe, right? But how do you write a base dissociation equation? How do you write a base dissociation equation? Yes, every time the base dissociation equation, if you want, you just add one H2O, because base means they were accepting H plus, right? So you have to show the base dissociation reaction as F minus is accepting H plus. So if there is no species to donate H plus, you can just consider water. Water is giving the H plus. Okay, so F minus taking H plus from water, so the formed species will be HF and OH minus. So this is the corresponding ice table for F minus. Okay, so here what is your I initial concentration? We have 5 mole. Again I am telling, this is mole, number of moles. That's not we need. Number of moles over volume, V total. You can take number of moles V over V total. This is H2O liquid, you don't want to consider. And this is 0, this is 0. Then change, you can consider minus X and X. And here the equilibrium is, yes, 5 minus X. 5 over V total minus X. 5 over V total minus X. Correct? And here it is plus x. So what will be the result of our ice table? X square over 5 over v, that's I'm just taking I, okay, because minus x we are usually omitting, right? So 5 over v total will be just initial concentration, like that I'm taking I, so is equal to this quantity I'm just giving like I, actually 5 minus v, okay, right? Or don't want any confusion, this is not I, what I meant is this one is close to I, okay, right? So this is our x square over I is not Ka, isn't it? It's not Ka, this is not acid dissociation constant, which is this is actually Kb. This is base dissociation equation you done, Kb. So what is Kb? Like, how do you get the Kb value? They will not provide any Kb value. They will give only Ka of HF. So we know that Kw, right? Kw, water ion product divided by the Ka will give a Kb, right? Water ionic product value is 1 times 10 to the power of 1 times 10 to the power of negative 14, isn't it? Divided by Ka you can do, so that you can get the Kb. In that way you are solving X. Huh. Is that the negative? Then you just negative logarithm of X, is it? Again one more step you need to do. Why? Because this X is not H plus. Correct? This X, see the X. What is this X? This is OH minus. So what you are calculated is OH minus concentration. So how do you do? The pH, pH 14 minus negative logarithm of OH minus concentration. That OH minus concentration is X. You are calculated X. Clear? So this is the way you have to do for the pH determination. Okay. See how many steps you done for this endpoint. In the previous case it was very simple, just 7. Don't want to do any calculation. But this time you need this much of calculation. Why? Yes, because the salt, this F minus is the reason for this much of steps, right? So first you are calculating because it's a weak base, you need to calculate the ice table. From the ice table we are calculating OH minus, and then we are calculating the pH. Okay, it's simple, right? It's just simple. The concept is very clear and very simple, but the problem is you need to understand these, and these are the things. F minus is this one, that one, like that. The idea have to be there. The concept, if it's clear, everything is okay. Okay, that's it. So that's the thing, endpoint calculation. So if in your question, if it's endpoint, this much of step have to do for pH determination. Before endpoint, your solution is always a buffer. So you can use the Henderson-Hasselbalch equation. Okay, right. Then what happens? 7 mole, it's not 5. 7 moles of NaOH is added. What happened? So 7 mole, yeah, before reaction 5, 7, 0, 0. After reaction 0, 2, 0, sorry, 5, 5, right? Okay, 5, 5. So this time who determine the pH? Yes. Is it NaOH? NaOH is there. So don't you want to consider the F minus, because F minus is any so have some effect. So do you want to consider the F minus effect? Actually, no. Why? Because F minus is, after all, it's a weak base, right? It's a weak base. NaOH is a strong base. So in front of NaOH, NaF is nothing, right? This is a strong base. So in front of NaOH, you don't want to consider the NaF. So this is the only time you can ignore the basic salt effect, right? The previous case, every time we took the effect of base, like we can't neglect the effect of base, isn't it? Like NaCl, we can't neglect the effect of NaF in any of the previous case, but this time you can. Why? Because in front of NaOH, F minus is nothing, so you can ignore. Only this time you can ignore the presence of NaF. Okay, so how to determine the pH? As usual, same way. Like, it's a strong base, so you can calculate the negative logarithm of OH minus, which is it's not 2, 2 over V total, correct? That's it. That will give the pOH, and 14 minus pOH will give pH. That's all. So that's all of the titration. So see the curve difference. Initially we discussed the case 1 was this one. It's a strong acid, starting with a strong, since it's a strong acid, the initial pH was very low. And yeah, this is our endpoint, right? This is our endpoint for the first curve, and this is our equivalent, that many volume. This is the pH, like 7 we got at endpoint. So maybe you are added some 20 ml. I'm just taking like a 20 ml will be the endpoint. Okay. And the second case, see the difference? One of the MCQ definitely will be this one. If you are replaced a strong acid with a weak acid, any change in equivalent point, like any change in volume of NaOH. What the question? If a strong acid is replaced by weak acid, or weak acid is replaced by strong acid, is there any change in endpoint, like volume of NaOH you are used for getting the endpoint? See, no, correct? It's both of them. The endpoint is 20 ml, because the number of moles is same, like, right? The number of moles we are taking is same, correct? That's it. So HCl is, if it's replaced by HF, the same concentration we are, if the same concentration is same, then same endpoint will be there. Okay, but pH will be different. At endpoint, see, strong acid, the endpoint is 7, but weak acid, the endpoint is greater than 7. Why? Because endpoint, always the pH is determined by salt. The first case you got a neutral salt. In the second case you got a basic salt. In weak acid, strong base titration, you got a basic salt. That's why you got a pH at endpoint as greater than 7. Greater than 7. Clear? Okay. As I told you, like the before pH, see here some extra points are there. You need to think about that extra point. See, this is our initial acid molarity, right? So here we have initially, so I'm just taking HA, right? And at end point, salt will be there. So salt means that A minus, like in our example, F minus, correct? And also this is what is this point? If 20 ml is the end point, then 10 ml will be, that is our halfway point. Okay, the titration curve is very, very important. The questions are mainly this from this curve. So be careful. See, this is our halfway point. Halfway point means pH is equal to pKa. Correct? And what are the species present here? Before halfway point, see, before end point, always the solution is a buffer. Correct? before the thing, so I can just uh, erase all these things so that will make a clear picture. For endpoint, so this is 7 and so greater than 7, correct? Will be the endpoint, okay? And this is our volume of NaOH added, and this point you can consider like a halfway point. So before the equivalent point, the mixture is a buffer, right? Before the equivalent point, the mixture is a buffer. After the equivalent point, the mixture is a base, right? And before the titration, like initially there is acid, correct? So acid is our HA. After the titration, what happened? There is a mixture of HA and A minus, correct? See, at this point, this is HA is equal to A minus. Is that the peak halfway point? Do you remember? HA, the excess HA, when it be equal to the formed A minus, that is what we called a halfway point. So before the halfway point, you can say HA will be in higher amount than A minus. And even base is completely consumed, base is not in the picture, right? Base is completely consumed, base is 0, okay? And at halfway point, HA is equal to A minus. After halfway point and before the equivalent point, what happened? Here HA will be lesser than A minus, and at equivalent point there is only A minus. After the equivalent point there will be base, okay? A minus is also there, but we don't want to consider A minus effect because I told you in front of strong base like NaOH, A minus is nothing, okay? So the species are also very important. Initially who is there, after before the equivalent point the solution is buffer, and the amount is also very important, okay? Halfway point H is equal to A minus. Before halfway point H is higher than A minus. After halfway point H is lesser than A minus. At end point only salt will determining factor, and after the end point base and salt will be there, but base is the determining pH determining factor, okay? So this is the whole stuff. That's all for today's video. I hope your all doubts are done. So if you found this video helpful, don't forget to like, subscribe and hit the bell icon so you never miss an update from Anu's Chem Corner. Got more questions or topic you want me to cover? Drop them in comment below. I would love you to help you out. Thanks for watching, and I will see you in the next video. Keep experimenting, keep learning. Bye.